Assalamualaikum. My name is nursyafiahmuhdikhwan Ikhwan. My student ID number is 2017687228 and my supervisor for my final year project is Dr. Rizal Effendy Mohamad Nasir. Today, I will present about my proposal for final year project entitled Development of an Emergency Medical Response Multirotor Drone. My presentation today will consist of the project background, introduction, literature review, problem statements, objectives, scope and limitation, methodology, expected result, preliminary outcomes, and project planning. So for the project background, we know that nowadays, various types of UAV, which is unmanned aerial vehicles, have been designed and developed to meet the needs of today's with different type of application. The variation of the specification is conceptually designed to meet the different type of application of the UAV, which have their own constraint in the matter of maneuverability, flight endurance, and flight range. Parametric study of the UAV specification will be done based on different brands of VTOL UAV in the market to find the optimum specification for this final year project. The design of the VTOL UAV will be done using a 3D modeling software which is OpenVSP, which is developed by NASA. After that, aerodynamic, static stability, and performance analysis will be done to create the most optimum and stable VTOL UAV. From the result obtained, a new efficient VTOL UAV will be designed to meet the emergency medical response needs. This slide shows the various types of UAV that exist in market. The first one is the zipline, which is used for medical product delivery. The second one is carbonic volante 3E, which is specifically used for aerial surveying. And the last one is DJI Agras T20, which is specifically used for agriculture application. Introduction section. Vertical takeoff and landing UAV, which is VTOL UAV, has both characteristics of fixed wing and rotorcraft UAV that enable UAV to take off and landing in vertical direction without the requirement of runway. During horizontal flight mode, the VTOL UAV will act like a fixed wing UAV, and during vertical flight mode, the VTOL UAV will act like rotorcraft. The advantage of VTOL UAV is it has longer endurance and longer distance to fly. It has the capability. In addition, it has the capability to hover as multirotor and cruise like a fixed-wing aircraft. There are two types of VTOL UAV configuration, which is the first one is converted plane. Converted plane is an aircraft that persists in horizontal reference line during takeoff, hover, cruise, and lands. While the second one is tail-seater UAV, which is the aircraft that tilts forward by utilizing differential control surface or thrust to gain horizontal flight and vertically take off and lands on its tail. For the literature review section, I have done a parametric study regarding the specification of the UAV from around the world, which involves 32 UAV in the market. So the first figure shows the graph of wingspan versus the weight of the UAV, which includes the maximum takeoff weight of the UAV, empty weight of the UAV, and the payload of the UAV. Based on the graph, we can see that most of the UAV has a wingspan of 2.5 meter to 3.5 meter. Then, mostly, the maximum takeoff weight of the UAV is between 10 kg to 20 kg. Moreover, from the trend line shows, we can see that the payload of the UAV is mostly 15% from its maximum takeoff weight. So, based on this graph, we can see that if we assume the wingspan to be 2.5 meter, the maximum takeoff weight of the UAV will be 10 kg. Next, this figure illustrates the graph of wingspan versus maximum endurance and the range of the UAV. From the trend line shows in the graph, we can say that the endurance and range increase as the wingspan increase, and we can say that mostly the UAV has the endurance of 1 to 3 hours and a range of 100 km to 200 km. So from previous assumption, if we assume the wingspan will be 2.5 meter, the estimated endurance will be 2 hours 15 minutes with the range of 160 km. The next graph shows the graph of maximum take-off weight versus maximum endurance and versus range of the UAV. From the graph, we can see that as the maximum take-off weight increase, the range and endurance also increase. So as we assume earlier, if the wingspan is equal to 2.5 meter, the maximum take-off weight is equal to 10 kg. So if the maximum take-off weight is equal to 10 kg, the estimated flight range is equal to 160 km with an endurance of 2 hours. We can say that this is a good rough estimation because the estimation value of the endurance and range with respect to the maximum take-off weight is quite similar to the estimated value of the range and endurance with respect of the wingspan. The next graph shows the relationship between the maximum take-off weight versus the cruise speed of the UAV. From the graph, we can see that the cruise speed significantly increased at first, but then the cruise speed will slightly increase as the maximum take-off weight increase. And from the graph also, we can see that most of the UAV have the cruise speed between 65 to 96 km per hour. As we mentioned earlier, if we assume the wingspan to be 2.5 meter, we can estimate the cruise speed to be around 72 km per hour based on the trend line shown from the graph. This pie chart shows the types of power system of UAV used. Mostly, the UAV use LiPo or lithium battery, which is 75% of the 32 VTOL UAV. In conclusion, we can use the result from this parametric study to design UAV that has the optimum performance that meet the requirement for emergency medical response. This table shows the estimated specification for the UAV based on the parametric study that has been done. For specification 1, if the wingspan is 2.5 meter, the maximum take-off weight will be 10 kg, payload equal to 1.5 kg, entry weight equal to 5 kg, battery weight equal to 3.5 kg. The expected range will be 160 km with expected endurance of 2 hours and cruise at the speed of 72 km per hour. And for the specification 2, with the wingspan of 3 meter, the maximum take-off weight will be 15 kg, payload equal to 2 kg, empty weight equal to 7 kg, and battery weight equal to 6 kg. The expected range for 3 meter wingspan will be 200 km with expected endurance of 2.5 hours, which is equal to 2 hours and 30 minutes, and cruise at the speed of 77 km per hour. The next section is the problem statement. Emergency situation requires fast response. Therefore, VTOL UAV is the best solution to avoid any delays due to traffic jams or narrow roads that encountered by land vehicle. VTOL UAV also able to overcome limited runways area for landing and takeoff, which is good for rural and mountains area, as well as longer endurance and high cruise speed. In addition, the spread of COVID-19 virus can be reduced with the use of UAV as it will eliminate face-to-face activity as social distancing is important to be practiced during this COVID-19 outbreak. Next, the objective of the study. There are 3 objectives for this study. The first one is to predict the parametric design for new VTOL UAV by investigating the parameters of existing VTOL UAV in the market. Next, to design a long-range and long-endurance VTOL UAV that meet the needs for emergency medical response. The last one is to evaluate the flight mechanics performance and stability of the VTOL UAV. The next section is the scope and limitation of the projects. My scope of project is to identify the VTOL UAV design that has the optimum requirement, which has highest flight mechanics performance and stability that able to fulfill the needs for emergency medical response. This study will involve the parametric study of previous existing VTOL UAV to conceptually design a new VTOL UAV, flight mechanic performance evaluation, and static stability analysis of the desired UAV. OpenVSP software will be used to illustrate the model of the design of the UAV as three-dimensional object, which can be used for aerodynamic simulation, static analysis, and flight performance by using VSP Aero software. The next part is the methodology of the project. Firstly, mission profile will be designed, and then we will identify the mission requirements. After that, parametric design will be done based on the parametric study that has been done during the literature review. After that, airfoil selection, and then the wing loading and control surface calculation. After that, we will do the 3D modeling by using OpenVSP software. After that, aerodynamic simulation and static stability analysis will be done by using VSP Aero software. And lastly, performance analysis will be done. For the mission profile, there are two mission profiles have been designed. So for the first mission profile, the UAV will unload the payload while loitering in the air. As we can see from the figure, the VTOL UAV will take off and climb and cruise at specific cruise speed at an specific altitude, and it will descend a little bit and loiter during the loitering. It will unload the payload and it will return to the original location after that. For the next mission profile, the UAV will unload the payload by doing vertical landing at the desired location. As we can see from the figure, firstly, the VTOL UAV will take a vertical takeoff, and then it will climb to a specific altitude and cruise at specific speed, and then it will descend and then transition from the horizontal flight mode to vertical flight mode, and then it will do a vertical landing, and the user will unload the payload. After that, the UAV will return to its original location. The next part is the mission requirement. The mission requirement for the UAV, it has the capability to hold maximum weight of payload of 1.5 kg and has the minimum cruise speed at 50 km per hour, have the endurance of 1 hour to 2 hours and 30 minutes, and the absolute ceiling required for the UAV is 200 meters above the sea level. The next part is a parametric design, which is a preliminary design process which is producing a new design based on existing parameter. The table shows two types of specification that has been done based on the parametric study that have been done. After that, we will select the airfoil. The selection of the airfoil of the wing is important because it will affect the lift to drag ratio, takeoff and landing performance, stalling performance, and altitude airspeed performance of the UAV. The next step, the sizing of the wing loading and the control surface will be done. Wing loading shows the amount of weight carried by a unit of wing area. In order to minimize the exert of stress during flight, the wing loading requires to be reduced as possible. After that, 3D modeling will be done by using Open VSP software. After 3D modeling is done, the aerodynamic simulation will be done by using VSP Aero software with the method of panel method. After aerodynamic simulation, the static stability analysis will be done. The static stability can be defined by the relationship between the angle of attack with lift coefficient and the pitching moment coefficient. Lastly, the performance analysis will be done, which will include the steady climb analysis, steady and level cruise analysis, maneuvering analysis, ceiling analysis, range and endurance analysis, takeoff and landing analysis. So the next part is the expected result. From the slide, this table will be used to illustrate the performance analysis of the UAV, and then the figure shows is the expected result for the aerodynamic analysis. Next slide shows the expected result by using VSP Aero software. The graph of the angle of attack versus total drag coefficient of the UAV expected to be like shows in the slide. The next picture shows the expected result for the pressure contour with trailing wake. The next part is the preliminary outcomes from the parametric study that has been done. So this slide shows the proposed UAV design that I have designed for the study. It has the wingspan of 3 meter, length of 1.9 meter. The wing chord of the UAV is 0.375 with the aspect ratio of 8. So the last part is the project planning. This slide shows the project planning that I have done for this semester, and for this semester break, I will do the aerodynamic simulation of the proposed design by using VSP Aero software. That's all from me. Thank you.